Hi everyone, welcome to our third lecture on Markov Chains and Processes. Today we're going to conclude our discussion of preliminary material that should mostly be review to you, and we will then begin the chapter on Markov chains, defining them, and we should be able to show one example today. So we're going to start today with an example from the content that we were working on at the end of the last lecture. So let's write our little example here. Let's suppose that we have some discrete random variable. We'll go with the usual name here. We'll call it x. So let's say let x be Poisson distributed with parameter lambda. And what we want to do is try to use the probability generating function, which we worked out in the last lecture, to find a couple of things to compute. Two different things, the expectation value of x and the variance of x, which I'll just define really quickly. I guess the defining form is to say that it's the expected value of the difference between the random variable and its expected value squared. So we'll say x minus the expected value of x quantity squared. But that's a kind of a clumsy way to write it usually, and instead we tend to write it as if you just expand that and then distribute the expectation value, you get the expected value of x squared minus the square of the expected value of x. Pretty familiar form. That's the easier form to work with, and that's what we'll use today. So we want to compute this using the proposition that we finished the last lecture with. And so I'm going to go dig that up now. So that was back in lecture 2. And the proposition had three parts, which I'll just steal and bring it over. So I'm just going to copy this over, and then we'll discuss it. So I'm going to put this over here on the side because it should be old news by now. I guess we can change its color to remind us that it's been stolen from somewhere and make it a little small. So we're going to use this proposition from last time, right? And so it has three parts. It says that if you evaluate the probability generating function at 1, what you recover from that is the statement of the honesty condition, and it's equal to 1. And the first derivative evaluated at 1 is the expectation value. And the second derivative is not the variance, but it has the pieces in it that are necessary to make the variance. I think in your notes you'll see there's I believe a corollary to this proposition that shows how to rewrite that, rewrite the variance in terms of the derivatives of the probability generating function. And we'll just go ahead and use that as we need. We'll just make it as we go. Okay, so for the first thing we're going to do is, we found before the actual probability generating function for a Poisson distributed variable, and so we're just going to use that. So we found the PGF, and that looked like this. So it was equals, don't forget the equals. It was e to the lambda times s minus 1. Right, so we worked that out from scratch. And so in order to find the expected value and the variance, we're going to need both the first and second derivatives of this quantity with respect to s, evaluated at s equals 1. So we'll go ahead and give this a try. So the first derivative of this guy, it's quite simple. All we do is bring down a lambda, and the quantity we're left with is actually the original function. So I'll just put that there like this. And that'll be handy because we know that the original function, the probability generating function, when you evaluate it at s equals 1, it gives you back 1. And now this makes taking the second derivative easier because we've already done the first derivative. Right, and so this is then just lambda squared. Like that. And you can see how this goes. Every next derivative would bring down another power of lambda. All right, so these are the tools we'll need to use the proposition. So let's just first write out the expected value. So from the proposition, which is over here, we have that the expected value, that should be the first derivative evaluated at 1. And so the first derivative is lambda times the original function, and then evaluated at 1. And that function evaluated at 1 is 1, also by the proposition, or you could just do it. And so this is lambda. Right, so that's the expected value. The expected value of a Poisson distributed random variable is the parameter of the Poisson distribution. All right, and now we'll do the variance. So the next step, the variance. So the variance of x, is equal to, we'll just write down that form again, the expected value of x squared minus the square of the expected value. And we already know the expected value. We just found it, it's lambda. So we could put lambda squared there right away. But let's just go on as is. And if you look at this form over here, and then just solve that for x, for the expected value of x squared, you get the second derivative of the PGF plus the expected value, right? And so this gives us the expected, sorry, I'll go back and look. The second derivative of g plus the expected value. Evaluated at 1 plus the expected value. Or you could explicitly make use of that corollary that's in the notes. It's the same thing. And then we subtract off this extra term minus the expected value of x squared. We can now put this in as lambda squared. And so now we just go up and look at what is the second derivative of the probability generating function. That's right here. So if we put in s equals 1, that gives us back lambda squared. So we've got lambda squared plus lambda minus lambda squared. And therefore we get back lambda, which is one of the kind of interesting aspects of the Poisson distribution. Its variance and its expected value are the same. That again should be a very familiar result to you. If not, you can go back and look in almost any textbook on Markov chains or any other kind of probability or statistics topic has a kind of a preliminary sort of chapter. And if you work through, they introduce kind of the most important distributions that you'll run into, like the geometric and the Bernoulli and the Poisson and so on. And you can work through what is the relationship between all those things. And if you are feeling rusty or worse, didn't know some of those terms, you should go back and do that. Okay, so now we'll make up we'll write out another proposition. All right, and we'll say that, let's say we have two random variables. So let's say you have for x and y. And I've been using, all the random variables that we've been introducing so far are discrete, and they have non-negative integer values. And so I'm going to write this as non-negative integer valued discrete random variables. Those things come up so often that it seems worth it to me to introduce that more or less ugly shorthand notation, but we use it so much. So let's suppose that you have this, and you're told if x and y are independent, so if they're also independent, and you should in the back of your mind, you should ask yourself, like, well, what does that mean? I remember something. If you don't remember exactly what it means, you can go back and look at your old notes. I think you might see this in 2504 or 2508 or some other equivalent for wherever you might have seen this first. But one way to write it, there's a couple of ways I think that are important to write it. One of them involves conditional probabilities. Those refer to events, so I'm instead going to write this in the following way. We say this means that the expected value of x times y is equal to the product of the expected values. But there are other ways to write this. So this is sort of just, a little thought bubble off to the side for you here. You should have some picture in your mind of what this looks like. So for example, I think you could, instead of x and y in there, you could be a little more, you can make a stronger statement and put not just x times y, but any function of x times any function of y in the argument on the left-hand side. And then on the right-hand side, you replace x and y by those functions. So you could write this in a variety of different ways. But again, it should be a familiar quantity or a familiar top concept, the independence of two random variables, just kind of trying to refresh you. So let's suppose that's the case, and you've got another random variable that's made out of these. So, and you have this random variable, which is the sum of x and y. Right, so that's the setup of the proposition. Then the following is true. The probability generating function for z is equal to the product of the two probability generating functions. Oops. The x goes down here. Like that. So this is a relatively important proposition that we'll use from time to time. I don't know if we'll use it today. Actually, no, we will. I think. Let's go ahead and do the proof. So a lot of times I'll do proofs in here, but a lot of times I'll say that they're in the notes or in a sheet. Sometimes I'll just leave them to you. But so here's the proof. It's not a wildly challenging proof, I think. But it has a kind of an interesting trick in it, sort of. So let's just write out the probability generating function so write out the left-hand side of what we're trying to prove. And then put in the definition. So what is the probability generating function? Oh, geez, it was so long ago. So it's this sum, like this, of s to the n times the probability that z is equal to n. So the probability mass function of z times s to the n. And if you stare at this long enough, or just remember from previous experience, you might recognize something here. So notice, oops, I wanted to use brown again. Notice the following thing. So if you don't remember it, so recall, you could go back and look it up. The expected value, well, this is not a big deal. The expected value, we saw this yesterday, or in the last lecture rather. The expected value of a function of a random variable, it looks a lot like what we see here. That is to say, it looks like a sum of things multiplying the probability mass function. And so we'll write that out. So sum over n, and I won't bother to write the boundaries. F of x equals n times the probability mass function. Like that. Right, so that's the expected value of some function of x equals n. And if you look at this generating function on the left, the form of this looks quite similar. There's the probability generating, the probability mass function is multiplying a very specific function of the argument s. And so what we have so this is a kind of a cool trick that you can use repeatedly. This is actually equal to the expected value of s to the z. Right, so that should be relatively familiar to you. If not, again, work through the preliminary parts of any of the textbooks that I recommended. Well, I guess not so much the hidden Markov model ones. Those might not have preliminary chapters. I can't remember. But if you work through exercises, you should be able to remind yourself of this. And so now let's just put in what is this thing? So s to the z, if you go back up here, so z is x plus y, right? So s to the z is s to the x times s to the y. Right? And it's kind of a clue. You should sort of see this coming. You've got something that goes from being a product to being a sum, and that happens when you go from exponents down. Okay, and so the next step is to separate those guys. So this is actually the expected value of s of x times the expected value of s of y. It isn't always this, but it's this way because these guys are independent. Right? And then that's the result, because the same trick that got us to go from here to here, or rather from here to there, we should now be able to write these guys, the expected value of s to the x. That's the generating function for x. And this guy is the generating function for y. And so we've got generating function for x, generating function for y. Right, and then you can write your little box over here if you like those, to say that your proof is done. Okay, so that's a handy little tool. How do you combine probability generating functions for random variables that have been added together like this? We'll use that a fair amount, often with sums that are not just two. Lots of different things, infinite sums usually. Okay, now we get to the last topic of the preliminaries, which is sort of the most, I don't know, ornate or interesting, maybe, I don't know. So we're going to introduce the concept of compound random variables. I think the notes might call this compound distributions. That's fine too. Okay, compound random variables, or compound probability generating functions, whatever you want to call it. Something is compound. So this is going to be our last topic before we dive into chapter 3 of the notes, where we introduce Markov chains altogether. But so this topic, we want to start off with a somewhat, I don't know, elaborate description, right? So suppose we have a sequence of discrete random variables. So consider the following. What we're trying to do with this is link up different types, two different kind of types of random variables. Well, you'll see here in a second. So suppose you have this sequence, x1, x2, and so on, up to x capital N, right? In such a way that the following, so such that the following is true, such that each of those things, xi, are independent, and each of them has a and has non-negative integer values, discrete random variable. I should have put valued in that. NNIVDRV. Pretty soon we just have the whole lecture can just be single lettered things smushed together. It'd be completely incomprehensible, and all would be perfect. Okay, so anyway, sorry, got off on a tangent here. So these xi's are non-negative integer valued discrete random variables, and they're all independent, and they're all identically distributed, or in other words, they have the same, you could say they have the same probability generating function by the uniqueness theorem. So we'll say with the same PGF, I guess I was using capitals for that usually, or sometimes at least. And we'll call that G with an X of S. And there's no index on that S to remind us that it goes for all of these Xi's, right? But now this is where things get a little bit interesting. So now suppose that capital N is also a random variable. And capital N is also non-negative integer valued discrete random variable. A lot of periods I'd have to put if I did that every time. Okay, so that's the setup, right? You have this sequence of random variables, and the number of them is actually also a random variable. So that's the concept. And we're going to straight away use this in an example to try to drive home why this was important. But so this is the setup, and now what I want to do is to define something that we just call the total. So define total to be the following. So this is expressed slightly differently than what you'll see in your notes. So we're going to say T, that's the total, is the sum from I equals 0 up to capital N. And we don't have an I equals 0, an x0 up there, so I'm going to invent one. X sub I. Right, so that's the total, is summing up all of these different x's, and I'm just forcing x0 to be 0. It's a little bit ugly, but it works, right? So we're going to say x sub 0 is a special one. It doesn't have that PGF up there. It's a totally different thing. It's just 0. All right, it's sort of a placeholder. Okay, so let's write out our proposition. What we're going to say is important about this total thing. All right, so here's our proposition, and then we're going to go ahead and use it. We aren't actually going to prove this. I think it should have a name, so I'm going to call it, this is just my own name for it. I'm going to call it total probability generating function. But I don't think anyone would recognize this proposition by that name, at least maybe not. And we're going to say the following. So let's suppose you have the above. So if above, that whole construct up there, with the additional property that n is independent of the x's, right? Then we're going to make a statement about the probability generating function for t. Then the following thing is true. The probability generating function for t has this kind of interesting form. It's the probability generating function for n, and then it's evaluated. The argument is the probability generating function for x. All right, so this is the origin of the term compound here. It's like compound functions. This g sub n is, its argument is g sub x, right? And this proof, we're not going to prove this. It's proved in your notes or in your sheets. Proof in the sheets or in notes. I think it's not the main slides kind of part of the notes, but the supplemental piece, the proofs. Okay. But so this is the important proposition that I want to make use of with this elaborate construct. All right, so let's go ahead and give it a use. So this is an application, essentially. Let's suppose you have a fish, right? Suppose you have a fish, an animal, that makes a bunch of eggs. Makes n eggs. Right? And it's a random variable, so we'll say n is, I'll give it a distribution, we'll say it's Poisson distributed. Right? You don't have to do that, but that's what we want to do here. And then we'll say the following is also true. In each egg it may or may not hatch And the probability of the egg hatching and making a little baby fish, each egg has a probability of hatching given by P. And they're all the same P. Right? And this is independent of N. That sounds sort of mathematical, but if you think about it, it seems plausible that biologically that might not be the case. If a fish lays 2 eggs, maybe they're really likely, maybe the fish put in so much energy into these 2 eggs that they're really likely to hatch. Whereas if the same kind of fish laid 50 eggs, maybe there's not the same. So it seems reasonable that you might expect this not to be the case. But so let's suppose that this little p is independent of the number of eggs that were hatched. Okay, so then we're going to define our little x's. Define these xi's to be identically, what do we call it? Independent, identically distributed. IID. I think that's how you do it in your earlier modules. Bernoulli distributed with probability P. Right, so these xi's are either 0 or 1. 1 is like a success, a hatch, and 0 is not. And so we'll say it's a fail. So we'll say xi looks like this, right? So it's 0 if egg I hatches. Oh, sorry, that's 1 if egg I hatches, and 0 otherwise. So these are a bunch of individual Bernoulli trials, which is kind of the starting point for a lot of your previous work, I think. Okay, and then we'll also, I just want to insert my sort of clumsy, awkward, we'll define x sub 0 to be 0. Okay, so this is the plan, or the construction of the example, and now what I want you to try to do is to find the probability mass function, or maybe you could even say not just the probability mass function, but tell me what is the distribution for the total, which is the sum of the x sub i's. Right, so what's the probability distribution or the probability mass function for the number of eggs that get hatched? Right, so that's what that total is, summing up all the successes. All right, so you can think about this for a while. There's a variety of different ways you could go ahead and solve this, of course, as always. But I think so you should sort of ponder it for a while. So maybe hit pause and think about what you would do. Maybe get out some scratch paper. Try to work some stuff out. And then unpause. And so what I'm going to suggest is we're going to try to use our alternate perspective. If you try to do this in a sort of a direct approach, or maybe a straightforward approach, it might be a little challenging. So try the probability generating function. Right, so that's the suggestion. All right. So what probability generating functions do we know? So n is Poisson distributed, so we've got that one. E to the lambda s minus 1, right? And the other random variables, the x's, the x sub i's, when I is not 0, those all are Bernoulli distributed. And they get this PGF is called G sub x. And you could look this up, or you could just simply write it down. There's only 2 variables that x can take on, 0 or 1. And so you can just, it's so straightforward, just write it down. So s to the 0 times which is 1, times the probability of 0. So we'll call that q. It's 1 minus p. Plus s to the 1 times the probability of s of 1, and that's it. There's no more. There's no more values. Sorry, did I say? Yeah, s to the 1. So n equals 0 or n equals 1. Those are the only 2 possibilities for this. And we have this restriction p plus q is 1. Okay, so we have those two probability generating functions. And so this is just an example that we've set up so that we can go ahead and just immediately use this theorem over here, right? Because this theorem is all about how do you make the PGF for the total. Right? So I guess there's not much mystery there. So this means that, so by the theorem or by proposition, I should even put in my hokey name for it, by the total PGF proposition. Did I call it a proposition or a theorem? Proposition. So by the total PGF proposition, the following is true, so that we can just write out the PGF for T. And it looks like this. So it's the PGF for N, and then its argument is the PGF for X. That's the idea. And then we just insert these different PGFs and see what we get. So I'm just first going to leave the N one alone. Or actually, let's do it the other way around, sorry. I'm going to evaluate the N one, and so that's exponential lambda times gx s minus 1. Right, so where we normally had s, we've now got g sub x of s. Right, and exp is exponential. For when I have a long argument, I'll just write it out that way. So I'm not trying to fit everything into a superscript. Okay, and then we just tidy this up. So put in the PGF for x. So we've got lambda times, and so this was q, let's take a look. Q plus s times p minus 1. And we're almost there, except I want to use q is equal to 1 minus p and eliminate the q. So I've got 1 minus p, all this stuff put together, the ones go away. So I get, p times s minus p. Or in other words, exp lambda p times s minus 1. And this tells us the probability generating function, and you know, as miraculously constructed example would have it, this is one that we understand, or we should be able to recognize. So this is the one that we've actually seen. So this is a Poisson distributed variable. So T obeys the Poisson distribution with parameter lambda times P. Right, so it's the same distribution as the X's had, but with a reduced parameter, with the lambda parameter, a smaller one. And I think this doesn't really answer the questions. The question asked, what did it ask me for? Find the probability mass function. So, okay, so you could look up the probability mass function for this guy and write it out. But that wasn't actually the point. We should probably have changed that. Okay, so that's the end of the preliminary material for us. That last part might have been a little new to you. I'm not sure. I think it might be, judging from the classes we offer here. But so you should all be kind of on a more or less level playing field if you rehash those preliminaries and make sure you understand them completely. And so for some of you that might take very little time at all, if any. For others of you, it may take sitting down with a textbook and rehashing basic principles and stuff, getting up to speed. But once we've done that, we can now start in on the main kind of bulk of the module, which is Markov chains. So this is chapter 3 of the notes, I believe. And I just thought I would start off with some sort of entertaining trivia. So if you look up who Markov chains are named after, it's a person, as I think I've said before. So it's, I don't know if you say this, Andre? I don't know how to speak Russian, obviously, so I probably really mangled that. But Mr. Markov, or Professor Markov, or Doctor, I'm not sure what his title was. He lived from 1856 to 1922. Pretty interesting period of time, I would say. And he's Russian. He was Russian. I think he lived in St. Petersburg, though it was called something different. And he, I believe, he definitely used Markov chains, or used chains for a particular problem. But I think this is the origin of them. So he used these chains for modeling the occurrences of consonants and vowels in some like corpus of literature. Used chains to model consonants and vowels. In some corpus. I use that word from machine translation. People use that word, and I guess also what's the other term? Machine translation people and natural language processing people use this for the body of text that they are using as their training data or test data or something like that. But so he looked at consonant vowels in a corpus of literature, Russian literature. It's kind of interesting if you have any interest in natural language processing or machine translation. I mean, he's looking at letters, so it's not quite the same. But, you know, it's some kind of text processing thing. But so that's the origin of this thing. The very first thing we're going to do is just define what a Markov chain is. And then we'll talk a little bit about this definition. There's sort of lots to say about it, obviously. Okay, so let's just make a definition. So a Markov chain is a discrete time stochastic process, right? So it's a type of one. So Markov chain, which I will often just call MC, is a discrete time stochastic process. And then we'll give some symbols to it. We'll say it's x sub t. So those are the random variables that make up the process, where t is equal to 0, 1, 2, and so on. And it has a discrete state space. So with a discrete state space, and the following property that we call a Markov property or a memoryless property. Same property gets more than one name. Memoryless property. Okay, and so let's write out what does that property mean. So here we go. So it says that the probability, this is sort of a long expression, that x sub t plus I has some particular value I of t plus 1. Oh, sorry, this is not t plus I. I've already mangled it. Jeez. X of t plus 1 is equal to I sub t plus 1, given that x sub t, and then we'll write out like the history of all the different x's, had some value I sub t. Next one would be x sub t minus 1, and I sub t minus 1, and so on, all the way until you got to x sub 0 is equal to something I sub 0. Right, so that's the left-hand side. So we want to say something about this particular conditional probability. So that's what the Markov process is about, or sorry, the Markov property or the memoryless property is about. So it's saying something about this thing. It's saying it simplifies in a particular way. And you can almost guess, I think, what it might be. Just from the name, I think from the name memoryless, I think you can guess it. But so it's almost all of this, so I'm going to take it, duplicate it, put it down here. Right, and so if it's memoryless, the conditional probability on like the next element in the chain depends only on the present, right? The current value in the chain. And so what we're going to erase is all this stuff. I'll just move this guy over. All right, so that's the memoryless property, right? So it says that this conditional probability on the next value of x only depends on the current value of x. It doesn't have any conditional dependence on the other x's. Okay, so that's the Markov property, or the Markov chain. That's the definition there. But before we really make much use of it, I should point out that this thing there are a lot of alternative definitions for this guy, and if you look around, in different books and so on, so I'll just say a note, you might find lots of different alternative definitions. So there's many, and they're all equivalent, or there are many that are equivalent to this. Many equivalent definitions. I think I found 5, at least. Just using a bunch of books I had around, looking up different definitions. There was one book in particular, I think, that had a list of 5. That's how I knew I could make 5 at least. And we aren't going to show you them all, so of course, obviously, then not also show that they're all equivalent. But I will show you one because we're going to use it at some point. So here's an alternative. So for example, an example alternative definition. Alternate definition for Markov chain. Now the beginning part is all the same. All right. So all this stuff about stochastic process, discrete state space, and so on. So I'm going to say it's all that same stuff, star, plus some extra information. So I'm going to go over here and label what star is. All right. So star is this stuff here, with the exception of the, so maybe I should, here, let's do this. And it goes up to here, right? And when, well, I guess you can leave that in there if you want. What we're going to do is rename what the Markov, what the Markov or memoryless property is. Yeah, so I should put that back, the whole thing. We're just renaming what the property is. So you could put this whole paragraph down there, and you can carry on. But we're going to add one little extra bit because there's going to be a couple of extra symbols present, or at least one extra one. So we're going to say that for any, oh, come on, eraser. And for any n and m, these are integers. I'll just be sloppy and not say so. Bigger than 0. The following statement can be made. It's a very similar one. All right. So here's the statement of the Markov property in this alternate definition. So on the left-hand side, we say x n plus m. Say that the probability that this is equal to k, given the following things. Xn is equal to in dot 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 down to x0 is equal to I0. And I'll define it in the same kind of duplicating way. So steal this guy, and then I'm going to erase its memory. So here goes its memory. Right? Now let's think about what this says. So what's different here is this guy, n plus m. So we're like m steps away from n. Right? And then over here, we're one step away from t. So this is a little bit different, right? So this is just saying the next one. And this one, there's a bigger gap, right? So we're just from n up to n plus m. And we say it only matters, this expression here reduces to this expression here. It doesn't mean that x sub n plus m maybe isn't different if you had, let's say, conditioned on x sub n plus 1. It might make that, then that one would take over. The point is, how do you phrase this? It's like it's the most recent point in the past, or the point nearest the present, or however you want to say it. So that's a different statement here. And if you look in various different textbooks, maybe you might find this being like the main one or something like that. Whereas I've written it as if you can only, when you strip away this memory, what you're doing is you're putting the present gives you the next step, whereas this is saying the point closest to the next step that you know about is all that you need in the conditional probability. So it's a subtle, it's a significant difference, but maybe a little bit subtle. Okay, so we're going to do our one little example problem, right? We've already done it actually. I just want to show you that it's a Markov chain. So I want to show that the gambler's ruin problem from lecture 1, gambler's ruin, so let's say show that 4. And then let's write out what is the gambler's ruin. I got to go dig it up. It's way back in lecture 1. And here's what I want to take about the gambler's ruin. So remember in that lecture it was called like example 2 or something. It's the only one where we kind of wrote out some equations that was sort of setting up the problem. And I'm going to steal those equations. So we say something about these x's. It's a dead giveaway. And this is the thing. We say that I'm going to steal. Okay, we go back over to lecture 3. And I'm going to paste it all just to remind us again that this is sort of stolen. I'm going to shrink it and make it brown. So this just to remind you, this is from lecture 1. All right. So what I want you to do, or what I want to do for this guy, for lecture 1, I want you to show that for this guy, the x sub n's are a Markov chain, or is, however you want to say it. Is a the x sub n's are, or x sub n is, up to you. It's a math class. We can have improper grammar. All right, so let's try it out. So we're going to just try to state, so we're going to use the, not the alternate definition, but we're going to use the kind of main definition. So I'm just going to steal it. Should I steal it? No, I'm not going to steal it. That's too hasty, right? So let's just think about what it is. I'm going to copy it over, right? The probability x sub t plus 1 is equal to I sub t plus 1, given, and then we'll write out the whole history here. X sub t is equal to I sub t, ... and then x sub 0 is equal to I sub 0. Okay, what does that actually equal to? Well, we can write it out because we have this rule so here's x sub n, and then it's written in terms of these guys. The previous one This is the dead giveaway. And this Z thing, and the Z random variables distribution has nothing to do with the past. It's only this thing here. So that's just how it's going to work. But so I want to steal that expression for x sub, in this case, t plus 1. So I want to use above with n being replaced by t plus 1. And if I do that, what I get is probability of, and now I'm going to rename this guy using this, right? And so I get x sub it was, so if n is t plus 1, n minus 1 is t. Plus, and again, n is t plus 1. Z sub t plus 1. So the probability of that is equal to I sub t plus 1. Given, and then the rest of this doesn't change, but I'll write it out. I better move that other thing out of the way. Right? So that's just rewriting the thing on the left-hand side. And if you look at the thing if you look at this conditional probability, right? Well, what do these things depend on that's on the right-hand side? Well, there's x sub t, that's there. Here it is. And then there's z sub t, and that's it. And z sub t is not in any of this, right? It's completely just this thing, sort of like a Bernoulli trial, except not 0 and 1, but minus 1 and 1. And so we can erase all that other stuff. And so I'm going to copy this over. Like that. Okay, and so that's our little example. So that's a Markov chain. It only depended on the previous, the conditional probability was the same if we dropped all the earlier part of the memory, because it didn't contribute. Okay, now we're going to finish off with one definition that we'll use a lot in the next few lectures. So this is just a definition. We're going to make a matrix for talking about probabilities for going between different states. So the states are like the i's, the indices of the x's. So let's say for all I and j in the state space, if x is a Markov chain, so that means all that stuff up above. And if t is equal to 0, 1, ... then here's our definition. P sub ij. And we'll put a little superscript of t in parentheses here. This thing, it's defined to be the probability that x sub t plus 1 is equal to j if x sub t was equal to I. See, these are the kinds of things that are important for the Markov chain because they just tell you about what is the probability of going to this other state if your previous one was something, or your present one or something. So these are kind of the only things we really care about. And so these are the elements of a matrix. So these are the elements or components, or however you want to say it, of something called the one-step transition probability matrix. One-step transition. Maybe probability is not part of that hyphenation. Probability. I think it is hyphenated with that. One-step transition probability and a bunch of them. Matrix. Right, so Pij are the elements of a matrix with a superscript of t in parentheses. So first of all, before I'm going to say one little thing about this. But before I say anything, I want to point out something funny here. You can always reorder the state space, right? So different i's and j's. These are the values that the x's can take, right? They're over here. But over here, these are indices of a matrix. And that makes you think, okay, there's rows and columns. And so, in fact, I better even label these. So this is, I'm going to do it in brown, I guess. This is the state that you go from, right? So this is from, and that's the row. And this is the state you go to, and that's the column, right? So what's funny here is that the i's and j's in principle maybe could be anything. It maybe is the case that they start at 0 or minus. Could they be negatives? No, they were non-negative integer values usually, but they could have been zeros. We can always remap these states so that they start at 1. This way, the sort of 1, 1 is the top left corner of the matrix. This is kind of where we start. All right, so note, this is just a potential pitfall with notation. Can and will always remap the state space so that it starts at 1, like that, right? And if you do that, then so that the Pij, T, so-called starts at row equals column equals 1. I hope that's clear why we did that. Okay, and now I'm just going to make one definition and we're done. So just a quick thing. So I'm going to say that a Markov chain is called homogeneous if there's no dependence on this for T on the left-hand side. All right, so let's say a Markov chain is homogeneous if the following, if for all different i's and j's, all different state transition pairings and t's, Pij T doesn't have any T dependence. So we'll say is T independent. That just gets called homogeneous. All right, that's all I want to introduce today. I'll talk to you next time.